this and cite that, or should I go about it like looking at the geostrophic and all the different flows? Or?
So the seasonal variation. So the Curcio. So in the Gulf Stream, one of the key questions you have is splitting up the the overturning circulation part from the horizontal circulation gyre part. And we have talked about some of the tools for that. In the Curcio, there's not an overturning circulation. There's just a gyre part. So then you're like, well, okay, I can do the gyre, which is basically homework 3, but then what? And so then what? One interesting then what is, what about variations from year to year, from month to month, season to season? Boshu at Hawaii, QIU, he's done a lot of stuff on talking about observations of seasonality in the Curcio and in the eddies on the Curcio and all of that. So he's where I would start looking. He writes a paper on that about every 2 years or so about some aspect of it, and they're all linked together. So you can kind of jump in and say, and so the echo model won't resolve mesoscale eddies, and most of what he's been talking about recently is the variability in the eddy fluxes. But even so, he still talks about the changes in the current and how that works, and the seasonal cycle of the winds and what that explains. And so those pieces are there. One of the big complications, which is related to what we're going to talk about today, is suppose you change the winds across the Pacific. So what's the cycle of events you think happens after that? So if you change the wind stress curl, then what?
Ekman changes.
That's going to change the Ekman. It's going to change the Sverdrup. But it's not immediately going to make its way all the way back around and like readjust the whole gyre. It's just going to be like going southward over here. So there may be a time lag in that response from one part of the ocean to the other. And in fact, we don't know this yet, but we're going to talk about this today. The way that that signal gets propagated around in the gyres is through a wave adjustment. So like you trigger something and it sets off a wave, and as that wave propagates, it adjusts to the new state of the ocean. The kinds of waves that are involved in that adjustment are Kelvin and Rossby waves on large scale. So Rossby waves propagate westward in the interior of the ocean, and Kelvin waves propagate around the coastline and up and down the equator. And so if you change like an eastern boundary upwelling system by changing the winds driving offshore Ekman and upwelling, the adjustment to that will propagate like a Kelvin wave. If you change the wind stress curl in the middle of the gyre, it'll make a little anomaly in vorticity, and a vorticity anomaly is a Rossby wave, or will trigger a Rossby wave response. And as that Rossby wave propagates around the basin, it will bring the gyre into adjustment with the new wind stresses. You could also imagine that it would be like an advective anomaly, like you put a little burst of flow, and then that flow has to make its way all the way around the gyre. It turns out that's just slower than waiting for the waves to do it. So the waves tend to get there first and set up an adjusted state. But that's not true of all systems. That's not true of like flow in a creek. So in a creek, like you know how there's big jumps in the flow, like it might crash down and then have a big breaking water thing that's just sitting there. That's a hydraulic jump, and it's actually there because the flow exceeds the wave speed. So the waves would like to propagate up and like change the upstream conditions, but they don't go fast enough. So the flow makes all of the signal propagation unidirectional, and that big bore, that jump, sits right on the transition between where waves communicate signals and the flow communicates signals. So there are similar effects in large-scale oceans where there's like hydraulic control is what it's called, but it's typically in deep overflows. But the balance of whether signals get communicated through advective processes or through wave-like processes is an important part of understanding how things adjust to time-varying forcing. We'll also talk a little bit about the meridional overturning circulation, and it had always been thought that that would be an advective adjustment. So say you make it fresher and it slows down the sinking, then it would have to slow it down all the way around the loop and back again. But now that we have a monitoring system out, it seems to be really highly variable for reasons we don't understand. So there may be some wave-like variability superimposed on that because the thing is just wobbling around a lot more than we expected. So we'll talk about that when we get to the MOC next week, I think. Okay? Other questions about? So that's a very long explanation too. Time variability is interesting in the gyres. But you could look for the change in the sphere drift, the change in the Ekman. So the Ekman would typically take an inertial period or so to set up, so like 12 hours. The sphere drift might take a little bit longer because it's kind of got to establish a vorticity anomaly, but it's an order of like weeks maybe. And the propagation of those waves across the basin might be measured in years. So you could expect the response of the western boundary current might be a little bit behind the changes in the wind forcing, and you can try and look for that by looking at, look for lag lead relationships, like a burst in the wind forcing. Does that then appear later in the Gulf Stream, the Kuroshio transport, that kind of thing. Other questions? Okay. All right, so large waves. Tides, Kelvin, Rossby. So Rossby we've heard a lot about, right? Rossby, the Rossby number. Kelvin is the temperature guy. And the tides are the tides. So this is sort of old school thinking about stuff, but we'll try and relate it to the gravity wave stuff that we talked about last time and see how these kind of waves are similar and different to the surface gravity waves that we talked about last time. So we talked about them fast and slow. Now we're going to talk about larger and slower waves. So in your brain, when you hear larger and slower, and you think of the Rossby number, what does that tell you?
Large, special Rossby number, but I think small temporal Rossby number.
So
Because it's changing slowly.
So the Rossby number is U over FL is the advective Rossby number. And so if L is getting bigger, it's getting smaller. And the temporal Rossby number is basically F times the time scale. And for a wave, the time scale is going to be the period of the wave. So it's F times the period. So what's the critical time when this hits 1? What is it?
What is the period of the planet?
Yeah, when it's the period of the planet, except this guy has a cosine factor in it, so it's actually the pendulum day, which is the Foucault pendulum's day. So how long does it take it to orbit? Because there's a cosine of latitude effect. Because our motions are horizontal, nearly horizontal, and so the important part of the rotation, the important part of the planetary vorticity is the F bit that will be setting a time scale for how long it takes for the Earth to spin you around, and the vertical is the thing that we want to usefully compare to the period of our waves. What's the period of our inertial oscillations?
12 hours.
Yeah, so it's F. So it's related to F. So an inertial oscillation has this equal to 1. That's the kind of thing that we're thinking about. And so you can have sub-inertial waves, waves that are slower than the inertial period, and super inertial waves. One example of super inertial waves are all the gravity waves that we talked about. Okay? So we're going to talk about some ways that you can force these big waves. And maybe the first way to think about it are tides. Tides are slower than, comparable to a day or slower than a day, because the day is the rotation period of the Earth. So it makes sense that you're going to get periods that are similar to the Coriolis parameter, which is also related to the rotation of the Earth when you think about tides. Because you're close to the moon, you're far from the moon. That's going to be wobbles on that inertial or slower than inertial period. But then there are also seasonal changes, and there are even orbital changes, Milankovitch cycles, which could conceivably trigger a wave. We're going to think about how that works. And then we'll talk about Rossby waves and Kelvin waves, which are the two classes. Okay. So wind forcing isn't really periodic. There is a bit of periodicity because there's a diurnal cycle in the winds, right? Like daytime land sea breezes are different from nighttime land sea breezes. And the seasons, it's usually windier in the winter than it is in the summer. Those kind of things do have some rough periodicity, but really the wind is kind of stochastic and noisy. It's not like a clean periodic forcing. But there are other clean periodic forcings, like perturbations to the solar cycle and perturbations to gravity. So why are we interested in periodic forcing? Why is that interesting when we're thinking about waves?
It's like a person on a swing.
It's like a person on a swing. You might have a resonant wave-like response at particular periods. And our whole business of these dispersion relations and stuff is really like intimately linked to thinking about plane waves with a particular well-defined period. So if we're using our conception of plane waves as we go along, if we have periodic forcing, it's going to be easily linked up to plane waves. Even though this stochastic forcing also drives a whole spectrum of wave responses, that's kind of a more complicated thing to think about. So the wind waves we talked about last time, it was like a whole range of periods from like hundredths of a second to hundreds of seconds in response to the winds. But these are going to be a little bit cleaner because you can say, well, there's a 12-hourly tidal cycle. What kind of wave does that trigger? We can go look for that wave and recognize it when it's there. Okay, so I'll just remind you, we have our complex wave writing a wave which has a phase speed, which is a function of the frequency and the wavelength. Or we can get fancier and put the wave number and the angular frequency and the regular frequency, and then we have a dispersion relation that we like to write this way, but you could also write it this way. They're the same thing. But we write it this way, omega equals c times k, because this makes it easy to recognize the phase speed, which is just omega over k, and the group velocity, which is d omega dk. And this form is still true even if c depends on the wave number. It still looks like this, but it's not guaranteed that those two would give you the same answer. If c depends on the wave number, we might have a group's velocity and a phase speed that are different from each other. And what kind of wave does that signify? Dispersive waves, because then the small waves or the long waves are going to get out in front of the other ones, and the group is not going to propagate with the same speed as the crest and troughs. So the crest and troughs might overtake the group, or they might be overtaken by the group. That's all to do with the difference between those two kinds of velocity. And so the dispersion relations we've looked at so far was the non-dispersive plane wave, which is just that formula except with a constant for the speed. And then we talked about surface gravity waves, which have this complicated tangent-based thing, but in the two limits of short surface waves or waves in deep water, because short we mean wavelengths that are less than the depth, or deep we mean much, much deeper than the wavelength. Those are the key comparisons. Then this is a good approximation to that formula, because that is the limit of kh becoming very small, and kh becoming very large, in which case tangent goes to +1. This one is the limit where kh becomes very small and tangent becomes just equal to kh. And so omega squared is k squared, because one k comes from out front and one comes from inside. G comes from out front, h comes from inside. So this is the long or shallow water surface wave limit. And this one is a non-dispersive wave with this group and phase velocity. And this one, remember, we have difference between the two. Okay, so that's our review section. So let's talk a little bit about tides, because this is kind of a fun one, because tides are periodic forcings, and they will excite all kinds of cool oceanographic things. So this is Mont Saint-Michel, which is an island part of the day, and a peninsula a different part of the day, in off the coast of France. And so there's a road that goes up here, and then there's a pretty monastery on the top and like a walled city, which is kind of cool. But you can go, and I've been, and you can take the tour bus in when the tide is low, and then you're stuck there until the tide changes, and then you better not miss your bus because you will get trapped for another tidal cycle if you don't get back. So all visits are in units of 12 hours, and that's the way it works. And as the tide comes and goes, in some places there is a tidal wave. All right, so tidal waves, tsunamis, not the same thing. So oceanographers now prefer to call them a tidal bore and then a tsunami rather than tidal wave, which got confused about both. But there are actually some places where when the tide comes in, it forms a coherent wave that you can see. So this is in the Chingtang River. But there is also one in Maine in the Androscoggin River that propagates up as the high tide comes in. And it's essentially the speed of this wave and the outflow of the river are in competition. And if the outflow of the river is fast enough to keep the wave propagating relatively slowly, it just comes like a wall of water as it moves up. So it looks like a tsunami or a tidal wave. But it is a tidal wave, not a tidal wave. Right? Okay. Yeah.
So will this wave fill in and then will not go back until 6 hours later?
Yeah, so it comes in and behind it, the sea level is just higher. So like the high tide approaches as like a wave front, a single crest that comes in and fills in the water behind it. It's not very common. More often, the tide just slowly rises, just kind of sinusoidally up and down. This is a weird effect that's a coupling between the river flow and the propagation speed of that wave in that basin.
So in a normal case, water just fills up and then goes down.
Yeah, and so there would be like an orbital velocity, except it's the tidal current that reverses direction throughout the day, bringing in extra water and filling up. So in Narragansett Bay, it brings in the water at part of the day, and then it takes it out at a different part of the day. So the directions of the currents out in the mouth of the bay connected to the ocean reverse to some degree throughout the day as the water's coming in and going out. Yeah?
Do you think of that as having a spring relationship?
Yes, that's what we're going to get to. If this were a plane wave, not in all this interesting topographic interaction, we could predict at that particular period a wavelength for different kinds of waves. And we'll see that it does actually work.
Even though, the tide is just bringing a wall of water.
Oh, yeah. So does this one have a dispersion relation? Well, it's definitely not a plane wave, although it is supported by a dispersion relation. This is a nonlinear superposition of a bunch of plane waves. So it's like this is a Heaviside function that in Fourier transform would have a projection across lots of different frequencies. And you can tell it's a relatively shallow water wave, so it's non-dispersive anyway. So the dispersion relation would look like a omega squared equals C naught squared K squared, but in fact the tide propagates as just a wall. It doesn't have the different constituent wavelengths are not separating from each other. It's actually worse than that because it's a nonlinear wave. So it's not even, you can't really do wave superposition on it, but even so, yeah. Does that make sense?
Sort of. It's not like a wave in the sense that we think of the other types of waves. It's not like the wall of water.
Or well, we have to be careful. We decided at the beginning that we wanted to be really careful about the way we defined a wave. A wave is a propagating signal which has a well-defined propagation speed, and it does not necessarily match the speed of the underlying medium. And so there is a river flow and there is a well-defined propagation speed. The water is not moving at the speed that the wave is moving, so it does qualify as a wave. A wave is not the crest, and a wave is not the trough, and a wave is not sinusoidal necessarily. This is a weird exception. A wave is this wall of water that's coming forward. So in this sense, it is a little bit more like a crest, but it's not, we wouldn't want to analyze it the way we'd analyze a normal crest of a sinusoidal wave because it doesn't even have really a wavelength. So yeah, so this is one of the ones that pushes the definition of what we mean by a wave away from a sinusoidal plane wave with a fixed period and wavelength. Okay. All right. Tides. So the tides are the response to astronomical gravitational forcing, mostly due to the rotation of the Earth and the revolution of the Earth and Moon. So there are two theories for tides. There's the so-called equilibrium theory, which says, let's just put the moon and the Earth and the sun in a particular configuration and figure out what the gravity field is, and then let all the water get sucked up to an equal potential surface of that gravity field and describe that. Say that is the tide. But the more interesting tide for our perspective is called the dynamic tide, because it's not actually an equilibrium response, it's a periodic forcing as the gravity field is wobbling around and around, and so it's triggering waves all the time because it's a periodic forcing, not an equilibrium response. And so in a place like Narragansett Bay, the moon is directly overhead the whole bay essentially at the same instant. But the tide actually propagates so that it's a few minutes different in Fall River from where it is in Newport, from where it is in Providence, because it's propagating as a wave as that signal of water incoming at the mouth of the bay propagates through the bay as a wave. Does that make sense? So we'll talk a little bit about this, but we should also just know what these pieces are. So there are two bulges in a tide. There's one on the near side and one on the far side in the equilibrium response. They can be due to both the sun and the moon. And there's something called the spring and neap tides, which have to do with the combination of those. So let's just think those through for a second. Okay, so here's the picture from Munch, which is sort of like got a lot of detail in it. The geometry of the subsolar point Q relative to that of a Zerber at point P. So anyway, so if you look up the zenith of the sky above you versus the place that's directly underneath the sun, there's a lot of geometry involved to think about how that would work. A little bit simpler diagram is to maybe think of this. So here is the sun and the Earth Earth's going that way. So there are two. So is the Earth in an inertial reference frame? It is not an inertial reference frame. It is being attracted toward the sun by the force of gravity. And so what balances the force of gravity? Exactly. The centripetal acceleration, or the centrifugal force, if you were in the frame of the Earth, is balanced with the gravitational force of the sun. So what that means is that there are two forces. If you want to draw it, there's a gravity force and a centrifugal force in the frame of the Earth, or there's a gravitational force and a centripetal acceleration in the frame of the sun. Okay? And that's helpful because when we think about the tides, we're going to want to think about both of those consequences. So here is the sun, here's the Earth and the center of the Earth, and here's the moon in this case. It doesn't matter whether we're talking about the moon or the sun, it's the same kind of effect. There's a bulge on the near side. Why is that? The water's attracted to the moon, and the force of gravity is a little bit higher here than it is at the center of the Earth. There is a bulge on the back side. Why? The Earth is being yanked out from underneath. That's the centripetal acceleration vision of that. That the Earth is being pulled harder. Or the centrifugal force explanation is this is the centrifugal force part of it due to the orbit of the Earth throwing the fluid on the outside. In the traditional physics classroom, they will not tell you the second explanation, they will only tell you the first explanation, but we are comfortable in rotating frames of reference, switching back and forth between centrifugal forces and accelerations in the inertial frame, because we already learned that. We had to learn that to get the Coriolis force in gear. So both of them are equivalent. You can either think of this as being a bulge because the Earth is being yanked out from underneath you, Or you can think of it as a bulge because of the centrifugal force from the orbit of the Earth, or the orbit of the moon around the Earth, in that, both of them in that coordinate system, about their combined center of mass. Yeah.
Is there no bulge related to the sun?
Yes, there's another bulge related to the sun. So we're getting that in a second. Sorry. And so this is just showing that the water would be getting sucked from the sides out to the bulges. Okay. Now we want to try and...
Okay, sorry.
No, here we go. The sun and the moon don't coincide. Okay, this is what this is. I don't even remember how to read this. I'm going to show you the movie. The movie's easier. Okay, here's the movie. Okay, there's the moon. There's the tidal bulge in purple due to the moon. And then there is a yellow tidal bulge due to the sun. The tidal bulge due to the sun is smaller because the sun is farther away. And so the difference in gravity from one side to the other is smaller. It goes like the cube of the distance. And the purple bulge from the moon is bigger. But right now, when you are at what phase of the moon? New moon, because we're seeing the dark side of the moon is exposed to us. The two bulges add together. And so we expect to have a spring tide, which is when the solar tide and the lunar tide are combined, and a new moon. And then if we move, if we move there, we are at a neap tide. There, we are at a spring tide. There, we are at a neap tide. There, we are at a spring tide. So the spring tides occur on the new moon and the full moon. And the neap tides occur on the waxing and waning moon, because it's just adding the two bulges together. So that's essentially, that is the equilibrium theory of tides. That's all you need to know. You can go through the details and figure out exactly how much the water needs to move to rebalance the gravity. You can do all those calculations. We don't need to do it. We believe it's there. Okay, so now tell me, what's the periodicity of those things?
Almost, but not quite the time it takes for the moon to go around one.
Exactly. So the moon to go around once, without including the amount that we go around on the year, is one part of it. But the Earth-Moon system is also going around the year. And a month is slow enough relative to a year that you can tell the difference. Those are different periods. The sidereal day of the Earth, the time that the Earth rotates relative to the fixed plane of the stars, is actually a little more than 24 hours. Does anybody know how long the solar day is?
The solar day is 24 hours.
Yes, solar day is the one we know about. The lunar day is actually a little longer too, because the moon is going around the same direction we're revolving. So you put these different pieces together and they all give you slightly different periods around 24 hours. What about the recurrence time on the spring tide, neap tide cycle? It's about a month, and so it's called the fortnightly tide, because a fortnight, every 2 weeks, is you go from spring to spring. So it's the cycle from full moon to new moon is about 2 weeks, so that's the fortnight part. And then the cycle to go back to the same full new moon is the month plus a little bit of the year, because you're actually wrapping around. So it's a little bit longer than the orbit time of the moon. It's the orbit time of the moon plus a few more degrees, because you've gone a little bit around the sun at the same time. Okay? Yeah?
Are the spring tides where the sun and the moon are not in the same direction later than when they are? Like, it's kind of like being tugged at both sides?
Yes, they're not the same magnitude. They're a little different, which is in the quartic contribution of the Taylor series of the gravity would be that part. And despite the fact that I have a PhD in oceanography and I've been teaching this for how many years, my mom still tells me that the spring tides are the tides that happen in spring. So, not everyone hears this, but spring and neap are why spring ever got in there is it's an odd naming. Anyway, okay, so what does this look like if, so the response, okay, so that was the equilibrium theory. So the equilibrium theory, does it single out like any part of the world from any other part in any meaningful way?
The poles.
The poles will be special, so there is some latitude effect, right? Because you're like, you know, in the same plane as the moon or not, in the same plane as the sun or not. So there'd be a seasonal wobble, there's some pieces there, but not like in the zonal direction. There's no difference between, say, Spain and Rhode Island, like in any real sense. But there are big differences in the tides from location to location, which is our first signal that there is actually a dynamic response to that periodic forcing. So this is 2 different locations in New Zealand, Foxton and Kaikoura, and you can see that this is just the tide record. You can see that it is radically different between the two. One has, so here's, what do we got? NF is new and full moon. So new moon, full moon, new moon, full moon. So you can see the spring tides are slightly behind the new moon and the full moon. So that's already a sign that there's a dynamic response, not an exact equilibrium response. And then these are showing the moon's perigee. So where the moon is oriented in the other plane, so as the moon is coming like this, up and down versus the plane of the sun, apparently that has a different response. So you can see different astronomical effects in different locations. So that means that there's something much more subtle going on than just equilibrium theory of tides, which would have, yes, it would have a perigee effect and a new moon and a full moon effect, but it would be the same everywhere along the same latitude. Okay, so let's try and understand a little bit what it's like. So this is a map of different parts of the world of whether they have a dominant semi-diurnal tide, twice-a-day tide, or a once-a-day tide. And all the green regions have a twice-a-day tide, including Rhode Island. But there are lots of places, like in the Gulf of Mexico and over in the Aleutians, that have a once-a-day tide. And there are other places that have a mixed tide, where they have a bigger once-a-day tide than a twice-a-day tide, but they definitely have both. So this is another sign that the dynamic response is something more complicated and interesting than what we would expect. So why does the tide vary with location? Tidal forcing is a global signal. Tidal response is a local signal, which depends on the bottom depth, the shape of the continents, and things like that. That's because the tidal response is really a forced wave. It's not an equilibrium response. You're changing gravity, and gravity waves are resulting from that. So if the gravity waves whose frequency matches that of the forcing is present in the basin you're in, you're going to get a big resonant response. So just like pushing a person on the swing, you push in the same period as the swing has, their amplitude grows. If you push twice as often as the spring swing frequency, it does not tend to work as well. And if you push erratically related to the swing frequency, the kid gets really mad at you and is like, "What's the matter with you?" So that idea of resonant, where you have a periodic forcing that's exciting a periodic phenomenon, is really important in the magnitude of the tidal response. So here are some maps of the amplitude of the tides, and you can see that some places have really big amplitudes and some places have very small amplitudes. And then you probably can't see them, but they're these spider-like white patterns. You can see those. And there are these points, and then the spider pieces are going out around the points. These points are called amphidromes. They're a place It is a node of the tide, and so they just sit still and the tide propagates around them. So there is something very peculiar going on. The tide propagates around them. Make sure I get this right. This direction in the southern hemisphere and this direction in the northern hemisphere. So there is something rotational of the Earth going on that is making this matter. So F is apparently doing something. So we have a kind of wave that is being reflected in the tides that has an asymmetry between the northern hemisphere and the southern hemisphere, and it tends to propagate around these sort of stationary points, and it obviously resonates in some places and not in others.
So the height doesn't change over there?
So, sorry, the map is the amplitude of the colors, but along the white line, they would be equal in phase. So say 2 hours after the moon is at its highest, it would be this white line, then 4 hours this one, then 8, and then this one. So it's propagating around as the day proceeds. And this is just a zoom in on amphidromes in and some of these equal phase lines near Hawaii. And you can see it's like a really complicated signal. And obviously this affects a lot of things. Biology is, here we're in a tidal marsh situation. Like a lot of the biology in the bay doesn't exist without tides. Where that's the town I'm from, also doesn't exist. The biology doesn't exist without tides. And if they change, they mess up a lot of things. So anyway. Okay, I'm just gonna skip this. You can predict the tides. You can predict them really easily empirically by just watching them and Fourier transforming the signal. And they are extremely repetitive. So you can make very good predictions for tens of thousands of years once you've watched them and constrained all those astronomical frequencies. But it's a little weird because like I said, the tide here happens at a different time from the tide in Fall River. So the predictions have to be different on a kind of micro scale. But how long after the peak forcing does the high tide arrive in Providence is easy. It repeats every single tidal cycle. It's mostly coherent with the forcing frequencies. Does that make sense, sort of? So this is the picture from lunch showing the power spectrum of sea surface height at Newlyn in the UK. And you can see that there are 12-hour peaks, 24-hour peaks, 6-hour peaks, 8-hour peaks, monthly peaks. So essentially all of those peaks are signaling different parts of the astronomical forcing. So they're all part of the tidal response, and it has this kind of wobbling signals that look like this, that have wobbles on slow, and then every 12-hour peaks inside. So it's all kind of superimposed on itself through this complicated wave-like response to all those different frequencies of forcing. All right. I'm going to skip that. All right, we got too much about the heat fluxes. Okay. I will briefly touch on this because there is a paleoclimate side to this. There are paleoclimatic astronomical changes to the orbit of the Earth. The tilt of the Earth's axis to its plane of orbit changes. So that's the obliquity. The distance of the degree to which the Earth's orbit is elliptical changes over time. And whether the elliptical part where you're closest to the sun, what season that happens in, the precession of that ellipse around the sun also change. They change on long time scales like 10,000, 20-something, 29,000, 40,000 years. Do you expect that to excite a wave response? So why do you say it's like an amplifier rather than a particular wave?
Just because the forcing is because of gravity, if it's stronger or weaker, that's
absolutely. So there is an effect on all the tidal forcing for sure as you go. But what about those periods of the waves versus like the slowest possible wave you can imagine?
It's just very slow.
It's just really slow. So it turns out that there's the possibility that a Rossby wave, which we're going to talk about in a minute, could go that slowly, but actually probably not. They probably aren't coherent that long. The whole flushing timescale of all of the world oceans is more like 2,000 years. So this is like just too slow to really excite a coherent signal. So the key time frame when we can excite periodic signals is from the like gravity waves that we saw, the kind of 100-second time scale, out to the monthly or maybe seasonal time scales when we would get excitation of waves. Beyond that, it starts to be difficult to get wave-like responses. But yeah, okay. And I'm not going to talk about Milankovitch, except to say that we already talked about it way over in the corner. Okay, let's talk about the waves themselves. Okay. So we have our shallow water system. This is the easiest one to study waves in. These are our two equations of motion. A momentum equation with the Coriolis force, not neglecting the Coriolis force this time, because we saw that things are different in different hemispheres. And we also think that these waves are forced on time scales where this might be order 1. And then we have the thickness equation, so the conservation of volume. If we just simulate those two equations, we saw this last time. This is just a plunger forcing the sea surface height to go up and down right there. And we get waves propagating away from the plunger. But if you can see, which you probably can't, these little arrows are signifying the direction of the current as the wave goes. The orbital velocities have to do with that. And they go outward and then circle around and then go outward again. Outward and circle around. The fact that they circle one particular direction is because of the Coriolis force. If I turn off the Coriolis, they just go out and in and out and in and out and in. But the Coriolis force gives you a sense of rotation. But the Kelvin wave is an even more interesting kind of rotating gravity wave. This rotating gravity wave has the same period as the regular gravity wave would. It just has that little bit of rotation added in. So it's kind of quantitatively different, but not so much qualitatively different from a regular wave in a non-rotating frame. The Kelvin wave doesn't exist in a non-rotating frame. It's peculiar to the rotation. So we take the same two equations of motion, and then let me draw a picture. Suppose we put some kind of barrier into our flow that would have a zero velocity condition through it. So our waves normally are sloshing around. We could say, oh, well, a normal wave might come in and reflect off the wall because of that no normal velocity. Kelvin, being Kelvin, thought, well, there's an interesting thing to say. What if we don't make that velocity zero just at the wall, but what if we just make that component zero everywhere? So that the wave only has flow in the direction along the wall. What if we just guess that to be true? It turns out that if you plug that into these two equations and linearize them, you get a wave equation out of it for the velocity in this direction. And it has a speed which looks like the surface gravity waves in non-rotating shallow water. But it's even weirder than that, because what does it do in amplitude in this direction? Remember how we talked about the Poisson equation and said it was oscillating in one direction and exponentially decaying in the other direction? You get the same kind of thing here, where the velocity signal is largest at the coast and decays as you go off when you plug in to solve that. And it actually turns out to be in one direction, the current appears to be in geostrophic balance with a decay away from the coast. So these are geostrophic flows with the sea surface height gradient highest right near the coast and decaying offshore. But then in the other direction, f of y plus ct, remember that's our non-dispersive wave. So we have a non-dispersive wave packet propagating along the shore. And then we have geostrophic velocity in the sea surface height decay away from shore. And it could go either way. It could go to infinity offshore, it could go to 0 offshore. And so if you throw away the solution that goes to infinity offshore, because that doesn't make sense, the wave can't be infinitely tall, then it selects for only one of the roots of this equation. And it's the one who propagates in a particular direction based on the sign of f. So the Kelvin wave in the northern hemisphere has a geostrophic current that decays from a sea surface height maximum near the shore. It's a non-dispersive wave that propagates with square root gh as its speed, and it only propagates with the coast on the right-hand side. It can't go that way. It only goes that way. And it's a very strange object that it only goes in one direction. And for my whole life, I had always wondered why that was. It's obvious if you get in the equations and you throw away that exponentially expanding whatever, but I had no sense of like the physical understanding. Brad Marston in the physics department and a couple of colleagues in France just showed that this is an example of a topological insulator, which is like a totally obscure thing from quantum mechanics, but it is a whole class of systems who have unidirectional edge waves as part of the way that the wave system propagates. So the Kelvin wave is a beautiful example, actually at macroscopic scale, of this effect that was also discovered in quantum mechanics, also discovered in solid state mechanics, also discovered in kind of gyroscopes and other weird sort of symmetry breaking theories. It's typical of things that have rotating effects or magnetic field effects in them. So this is a rotating, topologically formed wave. It has to be at an edge and has to propagate in the northern hemisphere with the coast on its right, and the southern hemisphere with the coast with its left. So when we think back to those tidal cycles, that's exactly what it was doing. It was running up, keeping the coast on its right as it was going around the amphidrome, or running around keeping the coast on its left as it was going around the amphidrome. Okay? I have more math here. Oh, the decay scale. How far offshore does this effect extend? We find another one of our favorite concepts, the Rossby deformation radius, comes back. That's the scale offshore that this geostrophic current that is associated with that tends to go. So it is a weird combination of all of the geostrophic ideas, but it's not geostrophic in this direction. It's only geostrophic in one direction. The other direction is kind of like a gravity wave. So it's an oddball kind of blended signal between geostrophy and gravity waves that is the Kelvin wave. Okay, so here we go. So if we have a Kelvin wave propagating, there's a high, it's propagating in this direction, the coast is over here. There'd be a divergence behind the crest and a convergence, there's a convergence in front of the crest and a divergence behind the crest. So it's not that the water is rushing along the coast. It's that the geostrophic velocities are setting up this convergence pattern. Actually, the along current, the variations in the geostrophic velocity are converging and diverging in front of and behind the crest in order to make the crest move a little bit farther ahead. It converges in front, which lifts the water. It diverges behind, which drops the sea surface height. And the other kind, a downwelling wave, does the same thing except it's diverging in front and converging on the back. So now, think about this in terms of an Ekman upwelling region. If we change the winds and we want to raise the sea surface height, this is just what we need to have happen. We need to have that convergence in to lift up the low anomaly. And if it isn't perfectly in balance, that little anomaly will just run away up the coast as a wave. If we need to reduce the winds, we might have, or sorry, this is the increase in the winds. If we increase the winds, we would have a bigger low at the coast. If we decrease the winds, the low at the coast would decrease some, and we would get an upwelling Kelvin wave. So this is involved in the response for those kind of things. Okay, so let's look at some movies. So this is the same as the plunger problem. I slowed it down some, and except I've now put it in a channel, so it's got walls on both sides. And right now I'm not rotating the channel. And so this is what you see if you see regular gravity waves, non-rotating gravity waves in a channel. They start out circular, they hit the walls, they get kind of more aligned with the channel as you go down away from the source. But if I rotate the channel, this is what you see. So clearly the Kelvin waves have a preferred direction. They propagate with the wall on the right. There's a little leakage this way, but it doesn't really form into a wave. It decays in a relatively short distance. So this is the kind of response that we would expect. And if you put the forcing right next to the wall, you don't even really get any response on the opposite wall. You just get little blobs traveling to the right of the anomaly along the wall. So it's a very weird kind of thing, yeah.
So this one has the plunger that's continually adding energy. At the ocean, would it just be one Kelvin wave, or is this a continuous, multiple crests?
Yeah, good question. So if we had periodic wind forcing, we could expect to see something just like this. It doesn't matter that it was a plunger or wind forcing. And actually the plunger, you could think of it as gravity wobbling, because essentially what you're doing is putting an anomaly in the sea surface height from its comfortable place. So the tides would be very much like a plunger. But the tides wouldn't be localized. They would be in a larger region. So that global tidal response is everywhere is getting pushed up and down, but the responses are coming out nearby the coast, nearby certain basins that have the right size, which I'm just about to show you. So if you have a basin where the Kelvin wave running around takes exactly the period to go around that the tidal forcing is, even though the forcing is uniform over the whole world ocean, and so it's sloshing in and out in a uniform way, that wave would resonate and would have a much larger response, because it would sort of get a kick every time it goes around. It would get another kick, just like pushing someone on a swing. Here is the Bay of Fundy with the amphidrome and the phase wheel drawn on top of it. These are the largest tides in the world. They have basically this forcing setup, so that the propagation speed of the Kelvin wave around the Bay of Fundy is resonant with the tidal forcing.
So this is something that's much slower, it's like an amplification of the tides?
So it's the tidal forcing is uniform, the response is not uniform, and in this particular place the response is very big because it's just the right size to have a Kelvin wave run around one time per tide. And so every time it goes around it gets a new kick from the tide. So that wave just gets bigger and bigger and bigger until it's saturated in its dissipation and that forcing. This Wait, which one is this? Hold on, did I just say that was the Bay of Fundy and this is the Bay of Fundy? You can also get one that, sorry, this is a regular gravity wave response. Oh, so this is showing one little outlet of the Bay of Fundy anyway, sorry. So here, the wave propagates, but it doesn't have enough time. The bay is too small. So there's a big signal at the mouth maybe, but then as you go in, it doesn't resonate. And so the tides, you get a wave that comes in and out, but it doesn't get resonated. It doesn't amplify by that. You could just track the passage of the high water line back and forth. And it doesn't have a lot of curvature, and it doesn't really show you the coming in on the right-hand side, going out on the left. Why do you think that is? What sets the scale of decay away from the shoreline? The Rossby deformation radius. So this channel is less than a deformation radius wide. And so essentially the response is not looking so much like a Kelvin wave because it doesn't have the decay scale away from the coast. It's just coming in and out. Here is the tides around New Zealand. So that is, oh, I wish it, sorry, I should have that on loop. So what hemisphere is it in? So is it the Kelvin wave propagating with the coast on its left or the coast on its right? Coast on its left. And it is quite clearly a Kelvin wave. It's not anything else. Like the Kelvin wave is the weird one that runs around the coast in that direction.
Is this measuring velocity or sea surface height?
This is sea surface height.
And they're related because of geostrophic balance.
And so the decay, this direction, has a geostrophic current in that direction related to it. So the convergence at the leading edge of this wave that lifts the sea surface height and the divergence at the back are variations in the alongshore direction of the geostrophic current in the other direction.
Can I ask one more question?
Yeah?
Can Kelvin waves interact with each other? Because I'm thinking they're kind of like a single file, and if you would generate another one, they would just all follow the same path.
So they're non-dispersive. So one never catches up with another one. They all travel at the same speed, at least if they have the same vertical mode. So they can be added to each other and subtracted from each other, but they don't one doesn't overtake another one to do that kind of interaction.
It's not like a resonance between them. It's only forcing.
The forcing and the Kelvin wave response, yeah. So we haven't looked at this kind of figure, but this is a way of plotting the dispersion relation. So this is frequency on this axis and wave number on this axis. And so this straight line is the Kelvin wave, and it has only a positive slope version. It doesn't have a negative slope version because it's a one-way wave. So it's kind of a weird thing. These are down here are where the rotating gravity waves are. And so our little KH, TANH, KH are all out here. But this actually includes the effect of the rotation on those. And when you do that, the fastest of the, the slowest of those, the one that's closest to the origin, is the inertial oscillation. So the inertial oscillation sits on that point. And you can't have gravity waves that are slower than the inertial oscillation. So the full rotating gravity wave system is much richer than the non-rotating case because you have the inertial oscillations, the gravity waves, and the Kelvin wave all superimposed on each other in different parts of the frequency wave number space. And if you are really careful about this and you're doing this on a rotating planet and you zoom in on the origin, there is yet another wave. And this wave is also unidirectional, but it's like way, way, way in the middle. This is the Rossby wave. And the Rossby wave has this funny kind of relationship, which is a completely insane dispersion relationship of 1 over square root of 1 plus r, the deformation radius becomes k squared. What does a Rossby wave look like? This is the same as the plunger problem, but instead of plunging, I just put an initial anomaly. And if you watch closely, let me restart it. If we watch closely, where I put it in the beginning, you see the Kelvin waves run away, but now look, that high anomaly is moving very slowly to the west, while maintaining a high anomaly with currents that are, going in this direction around the high anomaly. So what are the currents going around it doing? There's a pressure gradient force because there's high water and it wants to flow outward, but it doesn't flow outward. Why not? It's because there's a geostrophic flow around. So this is an anticyclone. It's a high. which is, so it's a geostrophically balanced motion, almost geostrophically balanced. There's a tiny imbalance to geostrophic imbalance, and it's causing it to drift systematically westward. The tiny imbalance has to do with the fact that this is actually, I put this on a planet, so this F is slightly larger up here than it is down here. So it's drifting to the left of the direction of increase of F, which is westward. And that is called a Rossby or a planetary wave. And you can go through the, we can go through the math, we're not gonna go through the math, but the math is there if you wanna look at it. And this is the dispersion relation, so omega equals minus beta naught times the Rossby number squared, kx upstairs, kx and ky downstairs in this completely insane. So even reading off the group and phase velocities off of this thing is kind of a nightmare. But we can do it more easily from that little graph. If this is k and this is omega, and the dispersion relation looks like this, oops, like this, what's omega over k? What sign is it here? Negative. What sign is it here? Also negative. Because omega is positive, but k is negative. So the phase speed is always less than 0. So what does that mean about Rossby waves? They always move one direction. I'm sorry, I should say this is k in the east-west direction. So they move west. The crests and troughs always move to the west. What about the group velocity? D omega dk. The slope here is positive. So this has d omega dk greater than 0. All through here, d omega dk less than 0. And over here, d omega dk greater than 0. For all of the long waves, the ones that are the smallest values of k, the long Rossby waves, their group velocity goes westward. For all of them of any length, their phase speed goes westward. And for the short waves, their group velocity goes eastward. So this is like full on. You can see why we took a whole day to talk about group velocity and phase speed and why it might be hard to understand. This is like the weirdest wave of any type that I've ever seen, because it has this very peculiar unidirectional propagation, and it depends on the amplitude as to what sign the direction of group velocity is propagated. So a really oddball wave. For the long ones, the really big ones, the phase goes to the west, so does the group. So you can imagine if we had, say, a Kelvin wave propagating along, it might be shedding Rossby waves off across through the interior to go west. Or if you put a wind anomaly here, you might get a Kelvin wave response that runs that way and also a Rossby wave response that goes west. Or the seasonal cycle would trigger a Kelvin wave seasonally and a Rossby wave packet that would leave seasonally. All those things happen. Next time we're going to see that there's actually a different kind of Kelvin wave that runs along the equator, like this, and it goes like this, and then it turns into a Rossby wave, and it goes like this, it turns into a Rossby wave, and it goes like this, and it turns into a Rossby wave, and it goes like this. That's El Nino. So El Nino is a resonant, semi-resonant Rossby wave, Kelvin wave response to wind anomalies that builds up into a 2 to 7 year oscillation of the Pacific. Okay. When we did the little discussion of the waves and the Kelvin waves, I didn't particularly point out that we were using the shallow water equations, and that would give us a square root of GH, but we could have also used the reduced gravity case. So There are both whole depth barotropic versions of these waves and baroclinic versions that might just be between the pictocline and the surface or just within the mix layer and the surface. So the propagation speeds differ depending on the vertical modes as well, which is sort of an elaborate second part of this story. In the echo model, the barotropic waves will propagate faster than in the monthly snapshots, so we just won't see the barotropic waves, but the baroclinic waves will propagate slowly enough that you can actually see them in echo. So you can track, for paper number 4, if you like, you can try and track these waves in the echo solution as they propagate around. And you can do this with a Hofmuller diagram. We're going to see some examples in, I think, a couple of slides. Let me show you this guy first. So this Rossby wave, we talked about it having a high with an anticyclone around it. And it also might have a low next to it with a cyclone around it. So why does it propagate to the west? You can sort of understand that by thinking about this. This is looking from above. So here's the present vorticity amplitude of the wave. So it has a little anomaly. You've taken a line of latitude and displaced it. So now your relative vorticity is anomalous because you're closer to the pole than you were before. So you're a little bit of an anticyclone. If you get pushed this way, now you're a little bit of a cyclone because you're off of your native latitude. This is sort of like how we talked through the sphere-trip relation. And if you're an anticyclone, you spin this way. If you're a cyclone, you spin this way. And now, what does this anticyclone do to this cyclone? It's pushing up, pushing up, pushing up, pushing up. So it's going to make this line of deviation in a little while be at the dashed line. And this cyclone is going to push down, push down, push down, push down, and make this solid line be like the dashed line in the future. Does that make sense to everybody? Now look, the dashed line is west of the solid line. So the wave propagates to the west. Yeah?
Sorry, I'm catching up. A Rossby wave is a variation in both depth and position in the north-south direction.
A Rossby wave is a vorticity wave, is one way to think of it. And so when we had conservation of potential vorticity, remember if you move poleward, you'd have a little bit of anticyclonic vorticity. You move equatorward, you have a little bit of cyclonic vorticity. So we're looking from above and we're thinking about that. But we also know that it's a geostrophic flow, so it would have a sea surface height anomaly as well. So you could perturb the potential vorticity either downstairs and have it be a height anomaly, or upstairs and have it be a vorticity anomaly, or actually in general both. So Rossby waves are potential vorticity waves. They're waves that are being restored back to the normal potential vorticity of your latitude and depth. All right. All right, we're not going to talk too much about the equatorial Kelvin wave. We'll talk about that next time. This is now the phase diagram at the equator that's got the Kelvin waves, the Rossby waves, the gravity waves, and some other crazy ones called the Yanai wave, which is another one we're not even going to talk about, but there's a lot of stuff going on. I want to close on this concept. Okay, have we ever seen these things in the real world? We know we have seen the Kelvin waves for the tides. That's clear, because you can just look at it in tide gauges. What about Rossby waves? So in 1996, right after we got our first satellite altimeters, Shelton and Slacks wrote this paper, and these are sea surface height anomalies. This is east-west direction, and this is time, and these are at different latitudes. And you can see that sea surface height anomalies are propagating which direction? Westward in time. And they are propagating westward at a different speed, at a different latitude, which is just what you'd expect from the beta and the dispersion relation, and a different speed. And everybody was really excited, and they made this, and they said, this is awesome. We have observed Rossby waves for the first time in the world. Here they are. The only problem is that they're going only half the speed we expected them to go. And so there was an enormous tizzy of like a decade of people working on this. And they went on and on and on. And then after a decade, Telton wrote another paper, and Slacks is in there too, where they said these are actually not Rossby waves. These are coherent eddies. And coherent eddies propagate similarly to Rossby waves. They're like a nonlinear Rossby wave. They're a big geostrophic anomaly, just like those crests and troughs. But they have a slower propagation speed than the plane waves do because there's a little bit of nonlinearity involved in their effect. And the way that is maybe the most convincing is that the eddies don't just propagate east-west. They actually get attracted to the pole that is of the same rotation direction of themselves. So all of the anticyclones are propagating towards the south pole, and all the cyclones are propagating towards the north pole. So there's a subtle drift. But they couldn't see this in the original record because they didn't have enough resolution in the satellite to tell the difference between an eddy and a wave. And by 2007, they had a constellation of altimeters, and they could actually greatly improve the resolution, and you can tell the difference. So we're now think that it may be not so clear that it's a Rossby wave and not a nonlinear Rossby wave or a mesoscale eddy. They're kind of mixed up together in some kind of way. So these things do exist, but maybe not in the linearized form that we think of with just the wave-like part that we've been talking about. So if you watch now, this is what the new satellites tell us the sea surface kinetic energy looks like. All these little guys are all propagating westward. They're propagating faster westward when you're closer to the equator. They're propagating westward down here too. When they're riding on top of the ACC, they're actually maybe propagating along with the ACC, not upstream. There's kind of like a hydraulic control question going on there. And they're propagating westward up here too. So they are Rossby wave-like. There are actually bigger waves that are propagating, longer wavelength waves that are propagating at a different speed that is not easy to see from this. This is picking out the ones that are kind of near the deformation radius and sides that have the most kinetic energy. But there's a whole superposition of waves in here. The larger ones, these are too small to be in the echo model, but the larger ones, the ones that are kind of this scale, will definitely be in the echo model, and they'll be triggered on seasonal and interannual variability, and you should be able to see them. And you can use that same Chelton and Slacks Hofmuller diagram in homework 4. I'll actually give you the code to make one of those from echo. So you can see the Hofmuller diagram of the waves propagating in echo. Cool. Next time we're going to talk about El Nino and how El Nino is a result of the Kelvin and Rossby waves, and also an interesting feedback with the atmosphere.